you have an image or a problem, a data set, sound, image, whatever data you want to learn, you handcraft features, you put them into some kind of classifier, and you get results. Now, the main issue for many years was how to create those features, and pretty much a lot of the machine learning area was called feature engineering, because most of the time, around 80 or 70% of the time, was spent on creating the good features or inventing new features, and pretty much using the same SVM or neural network or whatever classifier you want to solve your problem. Now, these things became a little more complex when the problem became more complex. For example, if I want to do object recognition, I have an image or sound, and I want to recognize what's ever in the image, I can't use simple features like in images, I choose usually lines or corner detectors. So more complex descriptors were invented, like sieve, hog, qubits, and things like that. You use some kind of quantization, because these descriptors are very large and you get a lot of them, so the description of the image using the descriptor could be multiplied the dimensionality of the problem significantly, so you use some kind of quantization to reduce the dimension, you do some kind of pooling which also reduces the dimension, and then again you use the same kind of classifier, or classifiers became a little better, but pretty much remain the same. By the way, everything I'm using is taken from presentations, and that's repeated by much more knowledgeable people, so you can look everything up. Very interesting things to read and look at. And then, actually a very long time ago, around almost 20 years ago, this guy, actually, Jan invented convolutional neural networks. It didn't work for many years for various reasons, computation powers, data, and etc. But 3 years ago, this whole deep learning, convolutional neural networks, so I won't break my teeth from now on, convolutional neural networks is CNN or ConvNet, with your permission. So it became very popular, again, mostly because data became more available and the computation power grew exponentially with the emergence of GPUs. So what are convolutional neural networks? Going back 6 years ago, neural networks are just fencing machine learning algorithm, where you insert data from one end, you propagate forward through the classifier, you get some kind of result, you compare it to the ground truth, to what you know is true, and you propagate back the error, and this way you train the neural network. Okay, eventually, at the end, the error is very small for the training set. Okay, so if you enter something and you get the same results, for example, putting in an image of a car and telling me, okay, it's a car, I know my network is pretty good, okay, thousands of images on a car. But original neural networks were very limited. So the idea behind convolutional neural networks, first, it's very good for images. Let's start with saying that. And most of the work I'll show here is on images. But the idea is, in CNNs and generally in deep learning, that you don't have to know what the features are. The network learns by itself what are the good features and uses them. How does it work? I'm not sure how many of you are familiar with image processing, but there is a process that's called convolution, where you take some kind of mask and you run it over the image, and you get the results. For example, if I want to find straight and horizontal edges in a picture, I'll run a kernel or a mask, and anywhere where it will detect a line, I will see a mark, and everywhere else I will see nothing. be black. Okay, so I'll get a black and white image with only straight lines, horizontal lines. And flip it by 90 degrees, the mask, I'll get horizontal lines. Okay, so these are usually, so my mask will show to be like this, so I'll get only corners. So the main idea is I'm taking the image, and the network does it by itself, but let's say it doesn't. I'm defining many filters like that. Okay, some are horizontal lines, circles, diagonals, whatever I want. Okay, only I don't need to define it. The network will do it for me. Very complicated how it does it, but if I had 2 more hours, I'd go into details, but we'll leave it like that. So what I'm getting here is basically a layer of the image where it has, for example, in this image, it has, I have 20 such images. I'm taking the image and I'm replicating it with different masks. For example, one of these images will show me only the horizontal line in the original image. One, the vertical lines, one corner, circles, whatever. This way I'm propagating it to the network forward. I'm getting some kind of result, same, not same, or getting some kind of error, propagating it back. And I won't go into all the details, but eventually at the end, what I'm getting is a set of filters or masks automatically. I don't need to define the features anymore. Hope you can see it. For example, a very known example in this field, the first layer, okay, it's called layers. This is the first convolutional layer, the second, third, and so forth. Now the networks are much larger than this one. This was 3 layers. Today, most state-of-the-art networks have 16 or 18 layers, a lot more than that. But for example, in this one, hope you can see here, the first layer shows very basic filters. Okay, for example, diagonal lines in some kind of colors, differences in colors. The second layer shows more complex filters. You can see, for example, here are all the corner detectors. Okay, you can see here circles, vertical lines, horizontal lines, sorry, the other way, those are horizontal, verticals. Okay, so the very first layers give me very simple features, very basic lines, circles, things like that. The more I advance up the layers, the features I detect become more complex. For example, probably can't see, but I can detect here some kind of textures. There are faces, dog faces, here are dog faces, eyes. Okay, the more I advance in the layers, the things I get, or the features I recognize in the picture become much more complex. Now, again, I did it, nobody, well, not me, but the man who built this network did not craft any of these features by himself. The network by itself learned to recognize those patterns in the images. Okay, so now, about 70% of the work, and that was 70% of the time that was used to craft features is no longer needed. So now all of the innovation goes into building these networks, improving them, and a lot more time is spent on the algorithmic side instead of handcrafting features. Now, what happens when we take this? Okay, so this is the features I'm learning. Okay, this is not what actually goes through the data, through the network. What actually happens is something like that. I have an image of the car. So when I run to the first layer, remember it's very simple mask. So the image will look pretty much the same as the first image. Okay, I can see some kind of blur in the image, some kind of lines. Okay, this is like blur, some kind of vertical lines, things like that. And the farther I go up, okay, the filters I'm using are much more complex. So in most places of the image, you'll see 0. And only in specific places, I'll see the actual detection. For example, I'm pretty much guessing, yeah, but this could be, since it's the lower part of the image, this could be, for example, the filter for wheel or something like the front side of the image. You can't really know. It's downside or scenes. You don't really know what triggered the detection. But at the end, what you get, like Alex said, you have a phase descriptor. Eventually, the phase descriptor would look like something like concatenating all the pixels here to one long vector. And okay, this is the description of the car. Okay, nobody can really trace that and say, okay, this is this car or it's that face. Okay, you could take this network and run a lot of images on it until you get something that's very close to this description. Say, okay, now I know this was the car. You'll have to run infinite amount of images until you get something close to it. So this was really the shortest explanation ever of convolutional neural networks without any of the boring mathematics or details. But this is really interesting. This is the one hardest topic on machine learning and deep learning and whatever. And the network is full of lectures, really interesting. This one, what I said here, reasonable, unreasonable effectiveness of deep learning. It's really interesting. There's it's 1 hour lecture by Jan Kuhn. Even for someone who's not really, doesn't really understand this field, it's really interesting, the non-mathematical parts of it. And okay, just what can you do with convolutional neural networks? So the most trivial things that everybody's doing right now is object recognition. For example, I get an image and you can't see it, but I'll tell you that it recognizes this image as a chimp or monkey or something like that, chimpanzee. So object recognition, object detection. I have an image and I want not only to recognize what's in the image, I also want to find where it is in the image, and keep that in mind when we get to something like that very soon. Scene parsing. I'm taking an image and I'm labeling each pixel in the image and assigning it some kind of label to what it belongs. For example, these are roads, this is a person, can't really see, but water, sky, building. Okay, it requires very, very good accuracy and a lot of details, but it's actually quite common these days to take things like that and parse the whole scene. For example, for self-driving cars, it's usually what it does. This is something very nice, which combines also a different kind of network. But if in this picture I only recognize an object, this is allowing me to describe the image in more details. For example, the description of this image is 2 pizzas on the stove, one with mushrooms and the other with basil. Okay, so this is probably the best example they had, so they're showcasing it, but it really does work. I don't know if any of you saw my talk on Bitcoin. I show different examples. This stuff works. I mean, it's very easy to fool, but it does work. And a lot more very, 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 very cool things you can do with it. Okay, this was the more theoretical, whatever parts of. Any of you have any questions? You have one.
I think 2 things. The one thing is, can you use today the CNNs on, for example, HANA or something in terms of infrastructure? Can you
on HANA? No.
Okay.
In order to train them, you need a lot of GPUs.
Right. Okay.
There's none.
Okay.
And we're doing it. I mean, we are creating things like that on the lab here, but we're not using HANA.
Right.
We just have a lot of GPU machines. Okay, so we'll switch to something we're doing. Actually, we are in the lab here, and We showed it yesterday in a big data conference, and it's logo detection. What we are trying to do, or we are doing, is identifying logos. You can see the SAP logo. Okay, it's marked here. Identifying logos in videos and images. Okay, you can see all the marks appearing now. It's not the best detection ever. We do miss a few, but we are on very, very early stages of doing this. And it actually didn't take a lot of work to create what you are seeing here, and it's relatively good, I think. Okay, so logo detection. This is not deep learning, this is not anything. It's actually very, very simple algorithm. It took me about 2 hours to run the first version. The algorithm in general is called Viola Jones. You might have heard of it. It's what all the cell phones use for face detection. Actually, the original algorithm talks about faces, but you can apply it to any object, and you have to train the classifier. But instead of detecting faces and detecting the SAP logo, there's a famous in the community of people who do computer vision example of someone who's detecting bananas. So that's very easy to train, very easy to create. The algorithm is very simple. Actually, it's almost stupid. It uses very simple classifier features. Remember, we talked about handcrafting, very complex features. No, it takes the simplest feature. It takes squares like this and just takes a window on the image, and it runs a lot of it, like 100 features like this, and at the end it says, okay, again, I'm talking about the training part. Does this window has a facing? No, okay. Going to the next window. Does this feature has a facing? No, and so on, until it finds a window that does have a face. And then it takes that configuration it used for these features and said, okay, if you pass each one of these features, tells me this is a face, and I have 100 of them. Okay, and let's say each one can detect the face in 50%. If I can pass the detection to 100 of them, each one gives me 50% accuracy, then my chance to be wrong is 1 minus 0.5 power of 100, which is almost 1. So the chances I'm wrong are 0. Okay. So this algorithm works very fast because these detectors are very, very simple, and there is some pre-processing on the images which I won't go into, but it works. It's really simple. There's a link here that shows a demo on YouTube. You can actually try face detection on YouTube with Viola Jones. See hundreds of movies later. Explain the algorithm, really simple if it interests you. So how does it work? Right now we are planning to offer this detection as a service. We have some kind of a web service built on an Apache web server with very simple HTML5 GUI. You can upload the movie. Right now it detects only the SAP logo, so it's not really interesting, but we will open it to other detectors. We'll be able to upload a picture of the logo. It will take a few days to train the detector, but after a few days we will be able to upload movies, and the detector will be able to detect this logo. All the detections are saved in HANA. We can calculate some kind of exposure metric. Okay, first we're trying to sell it to publishers or brands who publish on sport events or TV or whatever, and they want to know how much exposure their logo gets. Okay, because if I'm sponsoring a soccer stadium, I don't really know how much people at home are viewing my logo, or does it get good exposure, or does it get only like small exposure in the corner of the screen, or does it get like really big exposure in the center? Okay, you have no visibility for that, and we are enabling it. It's also possible to collaborate with other companies to do web crawling for events. but they only use text analytics. We can combine it with this for YouTube or whatever in the news to get more information about brands. And but this, as I said, this is very simple. Currently, we're able to detect a single logo. Okay, we can detect many, but you have to train each logo separately. We are working to enable multiple logos, but in order for it to run in reasonable time, it would have to use GPUs, which we are working on. We are planning, as I said, to provide it as detection as a service. And looking a little further into the future, we are looking to do it with deep learning. There are two use cases for this. In general, what you get is a lot of detections for each image. I won't go into it, but we have about 50% of the deep learning pipeline working right now with actually good results. But the harder 50% still have to work about the other 50% harder. And this is it about the logo detection. So if you have any questions on this, just really started with a toy example and actually moving itself to something like product. Doing a single logo on real time is not complicated. Very easy to do multiple detections, but one logo is not an issue. Okay, and you get very high results. And it's really not, I mean, one logo shouldn't be a problem with the product, although it's very not user-friendly. I mean, we don't want that each customer will upload their brand and wait for 5 days, and then, okay, something didn't work and we need to train it again. No, we want, like, if you go to the deep learning solution, you can upload 10,000 of brands or all SAP customers' brands or we need to pay for something like that. But it shouldn't be a problem to do it for multiple brands with deep learning. The last thing, oh, this is the wrong one. I don't even know what time it is, so I hope I'm not taking too much of your time. No.
11.
I'll keep it short, because I don't have a lot to show. Okay, so if you're familiar with the Kaggle site, familiar with it? It hosts a lot of data science, machine learning, whatever challenges. It provides a data set, a training data set, and provides some kind of testing the server, where you get the data, you train your model, and you test it on the test data, and there's a ranking and everything. So we just think 2 or 3 months ago when we started talking about deep learning and where SAP is looking to go in image processing, computer vision, one of the places we thought about is medical imaging. And just a week later, Kaggle came with this challenge where you try to estimate the progression of diabetes through images of the eye, because diabetes affects the sight significantly, causes the lesions in the eye. So they provide a data set of eyes like this. And what you see here is very small, scaled down images the original images are huge. They're like 2,000 or 5,000. Okay, also size varies significantly. There are very small images and there are huge images, which is a very big challenge. And I just randomly chose a few images to show you how complex this task is. There are 5 stages of diabetes. Just label them from 0 to 4. And just by looking at these images, it's very hard to tell which is which. I mean, you can see different colors because the images are taken in different different equipment, bad resolution. Sometimes the person moves a little. I mean, some images are in very good quality, some in very poor, different lighting. Some images are rotated, some of them are flipped. There are a lot of things that makes task very, very complex. I don't know, I don't even remember which is which right now, but these are the actual labels. Okay, I mean, if anyone can tell me actually what's the difference between 0 and 1, it would be nice because I tried to figure it out and I have no idea. Distinguishing 4, which is the latest stage, is actually easy because you see all these wounds in the eye. So distinguishing between 0 and 4 is easy. If you show me 2 images, I'm playing with this data set for 2 months. So if you show me 2 images, one 0 and one 4, we can probably distinguish it. But if you show me any 2 images between 0, 1, and 2, I have no idea what's the difference. So we're actually playing a lot with this data set. We are building a deep convolutional neural net to solve this problem. I'm currently ranked around 40 in this challenge, which is surprisingly good for me. I have a lot of ideas about to play with it right now, try doing basic things. But I can tell this is very, very challenging. A lot of fun, and if any of you is interested in machine learning or anything, I suggest to check out the Kaggle site. It hosts a lot of interesting challenges. And this is like our, I don't know, first step into understanding what our capabilities in medical imaging, because we don't really have data set medical images yet. We are planning to get one though. I don't have a lot to tell here. I can tell you later if you're interested about what the network and blah blah blah, but it's not really that interesting if you're not really interested. And just like tell you one more minute every time about what we are or where we are looking to go next. So it's pretty clear that there are some use cases for computer vision and medical imaging and things like that, but it's definitely not SAP's core business. Where deep learning is becoming very, very popular right now is NLP, natural language processing, text analytics, questions and answering, document classification, things like that is becoming very, very popular with deep learning, and SAP has a lot of business probably around this area. We are looking for anomaly detection, either in time series or fraud detection and things like that. Again, using deep learning, which are different models than convolutional neural networks. And this is it. So I think that in the future we are looking in 2 directions. One is text, deep learning for text analytics, things like that, and anomaly detections. And that's it.